All right, today we're diving into a really cool breakthrough in AI training. It's one that tames one of its absolute messiest problems and, pretty much by accident, unlocks this wild new superpower. We're talking about turning total AI chaos into a perfect internal map of the world. Okay, let's get into it.
So let's just start with a simple question. Take a look at these photos of birds. What if an AI with 0 labels could just tell you which of these is typical and which one is, well, weird? Hang on, because how we get to that answer is really, really cool.
Okay, so to figure that out, we got to pull back the curtain on a huge, messy secret in how we train modern AI, especially in what's called self-supervised learning. It's a problem that has been a real headache for researchers for years.
And that brings us right into our first section, AI training's messy secret. It all revolves around this major failure mode that happens when an AI gets a little too smart for its own good. It's a thing called representation collapse. So picture this. You're trying to teach an AI about cats by showing it a bunch of different pictures. But instead of actually learning the features of a cat, it just finds a lazy shortcut. It spits out the exact same answer for every single photo. It doesn't matter if it's a cat, a dog, a car, everything gets mapped to the very same point. I mean, technically it solved its task, but the model it learned, it's completely, utterly useless. So to fight this collapse, researchers basically came up with this whole toolbox of complicated hacks and tricks. It turned into this frantic game of whack-a-mole, you know? They'd squash the problem one way, and it would just pop right back up somewhere else. This made training models super fragile, really expensive, and just a nightmare to manage.
All this complexity, this mess, it finally led some researchers to just stop and ask a totally different kind of question. And that brings us to section 2, the perfect internal map.
Yeah, instead of just slapping on more Band-Aids, they went all the way back to square one. They asked a fundamental question. If we could design the ideal internal map of the world for an AI, what would it actually look like? What's the perfect structure?
And what they found, what they proved mathematically, is that the ideal shape is something called an isotropic Gaussian. Now, don't worry about the name. The best way to think of it is like a perfectly organized spherical library. Every single concept is a book, and it's placed so that it's equally easy to get from any one book to any other. No weird clumps, no big empty spaces. And this perfect organization, this is the key part, mathematically minimizes the chance that the AI will mess up on any future task.
And this really gets to the heart of it. On one side, you've got the old way. This clumpy, biased, distorted map where some ideas are all squished together for no good reason. And on the other side, the ideal, this perfect, uniform, spherical map. That became the new North Star.
Okay, so it's one thing to have this perfect target on paper, right? But how in the world do you actually get an AI to build that map? Well, that question leads us right into section 3 and a much simpler recipe.
The method they came up with is called SIGREG for short, and honestly, it's just beautifully simple. It's a 3-step dance. First, you project the AI's complex map onto a bunch of random, simple lines, kind of like casting shadows on a wall. Then, you test if those shadows look like a perfect bell curve. And if they don't, step 3, you just gently correct or nudge the AI's brain until they do. You just repeat this over and over, and it literally forces the AI to build that perfect spherical library.
And get this is the best part. The core of this whole thing, it's like 50 lines of code. 50! To replace that entire messy, complicated game of whack-a-mole we saw earlier. It's just so elegant.
And you remember that whole laundry list of tricks and knobs to tune from before? This method just throws all that out. It boils everything down to just one single key thing to tune. It is a massive, massive leap in just making things simpler and more reliable.
And the results? They're seriously powerful. This chart here shows LeJEPA trained on a specialized set of galaxy images. Not only does it do a great job, it actually beats Dino V2, a massive frontier model that was trained on billions of general images from the web. This is a huge deal. It shows that a smaller, smarter model, trained the right way, can actually beat a gigantic general-purpose model on its own turf.
So, okay, problem solved, right? We've got this elegant, simple, powerful method. But the story doesn't stop there, not even close. Which brings us to section 4, and this is where we find out about the AI's secret score.
This is where the researchers started to get a little curious. They started wondering, what if the process of forcing the AI to build this perfect map actually taught it something else? something they didn't even ask it to learn.
And this led them to ask a really fundamental question. Can you force an AI's internal map to have a specific shape, like our perfect sphere, without the AI also having to learn about the shape and the probability of the original data it was trained on?
And the answer they found? It's a big, fat no. It is literally impossible.
And this gives rise to this new thing they call the JEPA score. Okay, so here's the key idea, right? The real world isn't perfect and uniform. Some things are super common, other things are super rare. So to take that messy, lumpy real world and map it onto a perfect uniform sphere, the AI has to learn the probability of everything it sees. It has to figure out exactly how much to stretch the map for the rare stuff and how much to squash it for the common stuff. And in doing so, it accidentally becomes a master data statistician.
So, this AI accidentally becomes a master statistician. What can you actually do with that? That's what our final section is all about. Why this superpower matters.
Okay, let's circle all the way back to the beginning, those birds. Well, it turns out a model like Dino V2, which is built on these principles, can now do exactly what we asked. It can use this JEPA score to tell you which images are the most probable birds it saw. You know, the classic shot of a bird in flight. But it can also point out the least probable, the weirdest ones, like a bird just sitting in a strange place. And the craziest part? It learned all of this without a single human label telling it what's normal and what's not.
And you can see how this just opens up a ton of possibilities. You can use the score to automatically clean up your training data, to spot weird anomalies or outliers, to figure out if your model is ready for a new kind of data. You name it. It's this whole new toolkit that you basically get for free, just by training your model in a smarter way.
So, think about it. We started by trying to solve this messy engineering problem, and by finding this really beautiful principled solution, we didn't just get better models. We accidentally discovered they were learning a hidden skill all along. Which leaves us with one last kind of mind-bending thought. If an AI can learn to judge its own data, what will it learn to judge next?